Um, Welcome everyone to the 113th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Manuel Saorin from the University of Murcia in Spain, and the title of his talk today is On Set Generation of Parts of T Structures.
Okay, thank you very much. I thank Rudradeep for the invitation to give a talk here. And before I enter the subject, I will give some preliminaries, but that most probably all of you, by the audience that I see, most of you know. And then where a T structure in a triangulated category is just a pair of subcategories that satisfies these three conditions. The first one is that when you shift V by -1, if you think of complex state shifting to the right, then this is an orthogonal pair, meaning that each of the subcategories is orthogonal to the other one. Consists of the objects that are orthogonal to the other class. The second condition is that if you apply the suspension functor to the left part, that is usually called the aisle. So U is called the aisle, and V is the coaisle of the T structures. So if you apply the suspension functor to the aisle, then you are inside the aisle. On the other hand, the T3 said that any object in the category, in the ambient category, is in the center of a triangle where the left-hand side, the left vertex is in U, and the right vertex is in the coaisle shifted by -1. So it's a known fact from the start of this structure, due to Beilinson, Bernstein, and Deligne, that if tau is a T structure, then its heart, which is the intersection of these two classes, is an abelian category, and there is a canonical cohomological functor H from the triangulated category to the heart. This cohomological functor will be called the associated cohomological functor, or the cohomological functor associated to the T structure. From now on in this talk, all triangulated categories, this D will be a triangulated category with arbitrary set index coproducts. Then in this situation, when you assume that, then the aisle is closed under taking coproducts. If you restrict the cohomological functor to the aisle, then you get a functor which is left adjoint to the inclusion of the heart into the aisle. And third is that H is a cocomplete abelian category. A natural question that has deserved a lot of attention in recent years is the following: when is H a Grothendieck category? Of course, there are two sub questions, and then one asks when is H AB5, that is, direct limits are exact in H, and when does when does H have a set of generator? Just a moment. It's okay. When does H have a set of generator? So in fact, both sub-questions, except for very recent results, have been tackled when the ambient triangulated category has a model. For instance, when it is the homotopy category of some stable infinity category or a combinatorial model category. In such situation, you use a sort of ad hoc argument where essentially you take some set of generators of the model, and then via the localization functor on the homotopy category, which is your ambient triangulated category, and then you pass with the cohomological functor, you pass to H, and then the image of that set of generators in the model would be a set of generators in H. A recent result that does not use of Stovicek and myself does not use any model. The result said that if D is a triangulated category with coproducts and tau is a compactly generated T structure, then the heart is a locally finitely presented Grothendieck category, and moreover, if you take the compact object in the aisle, then the finitely presented objects of the heart are precisely those isomorphic to the objects resulting in applying the cohomological functor to the compact objects in the aisle. You see between bracket compactly generated here. You see this between bracket condition, which you can put without any harm. I mean, the theorem would be the same, because when you work in any triangulated category with coproducts, then if you have the tau a compactly generated T structure, then you take, for instance, the compact object in the aisle, which is a skeletically small subcategory, and then you take the triangulated subcategory generated by them, and then you are working in a compactly generated subcategory, and you have there a T structure where the aisle is exactly the same, but the coaisle is just the intersection with the subcategory, but the heart does not change. And then, if the result is true when the ambient category is compactly generated, the result is true in general. So I make emphasis on this because later on, what we are going to generalize is the result where you have the hypothesis that D is compactly generated. So the goal of the talk is generalizing the generation part of this, and then, I explained the terminology of on the theorem with Stovicek. So D is compactly generated, the triangulated category. When you have a set, it's very important that it is a set of compact objects such that the full orthogonal to S is the zero subcategory. That is, the only objects such that all morphism from S to shifts of Y is zero is precisely the zero object. In order to understand what is a compactly generated T structure, I will introduce what is the T structure generated by a set. So when you have a set in your triangulated category, you can form this orthogonal pair. So you take, on the right, you have all objects such that all morphisms from S to positive shifts of the object is zero. And on the other hand, so you have the same definition with negative shift, but you take the left orthogonal, where this pair satisfies condition T1 and T2. The only condition that is not clear that is satisfied is T3. Remember, it meant that any object in the subcategory is in the center of a triangle of this sort. So that is not guaranteed for the T structure or the orthogonal pair that I just introduced. But when it is a T structure, when you have this property T3, this T structure is called the T structure generated by S. So a T structure is compactly generated when it is generated by some set of compact objects. So far, I have introduced the terminology concerning in the triangulated world in this theorem, and you have also the abelian part corresponding to the heart. So an object of a cocomplete abelian category is called finitely presented when the corresponding covariant Ohm functor preserves direct limit. So as above, this cocomplete abelian category is locally finitely presented when the class of finitely presented objects is skeletically small, and any object, this equality means that any object in A is the direct limit of finitely presented objects. This blue mark that I put here is just to remind me that to say that this is equivalent to say that the category A has a set of finitely presented generators. And then we now recall some generalizations existing in the literature of compactly generated triangulated categories and of locally finitely presented abelian categories. So let's remind you some concepts introduced by Niemann in his book. Given any regular cardinal alpha, Niemann introduced the concept of alpha perfect class or set of objects in D. Roughly speaking, X is an alpha perfect class when given any family of objects with less than alpha objects in the family and a map from X to the coproducts of the objects, there is always a family of maps with domains in X indexed by the same set with the property that this composition, that the original F, the original map F, factorized in this way. There is another condition that I won't say explicitly, but it has to do with the vanishing of this composition. I mean, if you have a composition that like this that vanished, then you can create some elements of the class X in the middle so that you factorize this map in such a way that it is zero. But, well, as said, I won't say explicitly, it is not so important. Then the triangulated category is said to be alpha-compactly generated if it has an alpha-perfect set of generators consisting of alpha small objects. That is, objects such that when you take any map from X to a coproduct of objects in the category, then there is some subset of lambda, in this case, such that X factors, or so the map, this map, say F, factors through a subcoproduct of size strictly smaller than this is alpha. This is a mistake. Then the category D, the triangulated category D, is well generated when it is alpha compactly generated for some regular cardinal alpha. So some properties of a well generated triangulated category are the following. For each regular cardinal alpha, there exists a unique maximal class D alpha, which is alpha perfect and consists of alpha small objects. Such a class is skeletically small, and its objects are called alpha compact. D alpha, the subcategory of alpha compact objects, is a thick subcategory closed under coproducts of less than alpha objects. Then, whenever you have that alpha is less or equal than beta, alpha and beta regular cardinal, you have that D alpha is included in D beta. And finally, the whole category is the union of the D alphas when alpha range over all regular cardinal. In particular, a consequence of this last equality is that if you have a set included in D, then there exists a smaller regular cardinal alpha such that S consists of alpha compact objects. So, as an example, for an object X, lambda Aleph 0 compact is the same as compact and is the same as small, meaning that the covariant OM preserves coproducts. That this Aleph 0 compactly generated is equivalent to say that it is compactly generated. And just to show you an example of a well-generated category which is not compactly generated, the homotopy category of projective OR modules is Aleph 1 generated, but not compactly generated unless the ring OR is coherent. So we go now to generalization on the abelian part. So generalization of locally finitely presented abelian category. Again, A is a cocomplete abelian category. Given a regular cardinal alpha, a poset I is called alpha directed when every subset of size less than alpha has an upper bound. a direct system is called an alpha direct system when the underlying directed set I is alpha directed. The corresponding direct limit is called the alpha direct limit of the xi. An object X is alpha presentable when the covariant functor, the associated covariant functor, preserves alpha direct limits. And we denote by press alpha of A the subcategory of alpha presentable objects. Then the category A is called locally alpha presentable when the subcategory of alpha presentable objects is skeletically small, and each object of A is an alpha direct limit of alpha presentable objects. This is again equivalent to say that A has a set of alpha presentable generator. Of course, when alpha is Aleph 0, then you have exactly what we had before. Aleph 0 directed set is the same as directed set. Aleph 0 direct system is the same as direct system. Aleph 0 presentable object is a finitely presented object, and A is locally Aleph 0 presentable if and only if it is locally finitely presented. Okay, when we have this generalization, we remind you of a theorem of Niemann in a paper appeared in Transaction in 2018 that wanted to generalize a result by Leo, Ana, and Maria Jose Soto, where they proved that if you have a set of compact objects, then you take the smallest suspended subcategory, meaning that this is closed under positive shifts, that is closed under extension and arbitrary coproducts, and then it turns out, I mean, the result of Leo, Ana, and Soto shows that then this is the isle of a T structure. And Niemann wanted to show that not just for compactly generated T structure, but T structure generated by any set. So you take any set of objects, and then the ambient category should be well generated. But what it is important for me is not exactly that result, but in the paper it appears the following: let D be a well-generated triangulated category, S be a set of objects. You take he proved that exists the T structure generated by S, and then you take now the smallest regular cardinal, or the smallest of the regular cardinals beta that satisfy two conditions. D is beta compactly generated, and S, the original set S, consists of beta compact objects. So if you take the smallest regular cardinal alpha satisfying that property, then he showed that any object in the isle of this T structure, so any object here, is the Milnor colimit of a sequence where U0 and all successive cones are coproducts of objects of alpha compact objects in the isle. So this is important. This will be important for us. So our main theorem actually is the theorem. The talk essentially consists of stating the theorem and just outline the proof. So let D be a well-generated, and S is any set of objects. And let alpha be the smallest of the regular cardinals beta, such that D is beta compactly generated and S consists of beta compact objects. You take now a skeleton of this skeletically small subcategory, that is the alpha compact objects in the I. Then each object of the heart is an alpha direct limit of objects in H of S. So you apply to this S, you apply the homological functor, and each object in the heart is a direct limit, the alpha direct limit of these guys. And then the second is that the alpha presentable objects of H are exactly those. In particular, H is locally alpha presentable. Another consequence that I didn't write here is that then when the ambient triangulated category is well generated, any T structure generated by a set of objects has a heart which has a set of generators, even if the heart need not be in any case, in this case, AB5. So it's just a co-complete abelian category. So the case of alpha equal lambda 0 is precisely my theorem with Jan Stovicek. So I mentioned just at the beginning, when I state that theorem, that there was an in between bracket that was, so the theorem when you delete the bracket is equivalent to the general theorem. So what I mean, a generalization of the result is when you put here compactly generated, then the result that I try to prove now is precisely is a generalization of this part. Okay, this is the theorem. And now we go to outline the proof. So steps of the proof. The step one say that if you take the coproducts of this, remember that S is a skeleton of the class of compact objects in the alpha compact objects in the I. If you take P coproducts of these guys, then this is what is called a T generating subcategory of U, of the I. What does it mean? It means that it is pre-covering. And in addition, is that for any object in the I, U, you have a morphism from some object in P, such that the cocone is, this is the important thing, the cocone is again in U. I mean, when you go to the left, you don't have a guarantee that if you have a morphism between objects of the I, the cocone is going to be again in the I. This is even rarely the case, but in this case, you impose that whenever you have an object in U, you can create a morphism from an object in P such that the cocone is in U again. So the basic idea of the proof is that you have the U, you start with an object U for which you want to create this triangle here, and then you consider the sequence given by Neumann's theorem and the corresponding Milnor triangle. If you are able to construct for each UN, you are able to construct the desired triangle, so a morphism from some object in P whose cocone is in U, then you can guarantee the existence of the desired triangle for U. So I explain this in a moment. So, so you have your triangle, with the UN, you have 1 minus F here, and you have your U here. And now, because we are assuming that each UN has the triangle, so you have the coproduct of the map here, say Pn, and then you have some coproduct of objects in U, and then you create the homotopy pullback here, and then you get something here, some point here, but because of this construction due to the octahedron axiom, you see that this guy is in the middle of a triangle where the vertex, the outside vertex, are in U. So this is in U, and here, if you complete here by the octahedron axiom, so this is your desired triangle. If you call this U prime, U tilde, for instance, then this is your desired triangle. So the conclusion of this Okay. So the conclusion of this is that you can prove that it is enough to prove the results for all these guys, for all these UN, and then the proof goes by induction. So you can assume without loss of generality that U is a n-fold extension of objects in P, and the proof goes by induction on n, and actually it further reduces easily to the case of n equals 1. That is one extension of coproducts of. In that case, here is where come an argument which does not appear. I mean, it's different from the arguments that we use in the joint paper with the Stovicek. The key point is a very, I mean, to prove this, the existence, I mean, it is based on this morphism that you have here. The point is that any coproduct in any additive category with coproducts is the direct limit of the subcoproducts of less than alpha objects, where alpha is any regular cardinal that you could fix. In our case, is the one that appears in the statement. And then because the objects there are alpha compact, then you can arrange that in some way, in a way that this morphism appears as a direct limit of morphism. And all of these objects are going to be subcoproducts of these coproducts here. And then, I mean, it is not enough. I mean, this is quite clear that any coproduct is going to be the direct limit of subcoproducts of less than alpha object. But then you should arrange something in order to connect them, and you create really a direct system of morphism between the corresponding direct system. And what happened is that you express F as a direct limit of these guys, direct limit in the triangulated category. So in the triangulated category, it's very rarely the case that you have direct limit, but they are a special direct system. They are subcoproducts and so on. Okay, then you have that, and then using that, you can prove that essentially what you do is you take the cone of any of this guy, and then you can by passing in some sense to the direct limit, the corresponding cone is going to be really, it's going to create the morphism from a coproduct of objects of S to this one. Why is important this T-generating condition? You could ask yourself, why is this important? The important thing is because there is a proposition, actually in the paper is a theorem, but I put here as a proposition. If P is a T-generating subcategory of the I, then we have a shared quotient functor from the category of finitely presented P module. So just so say this is included in the category of contravariant functor from P to AB. So this is to be here means that you have a presentation of F like this. For some map. So sometimes they are called the finitely or the finitely presented functor, or we can call them the finitely presented P modules. So why is important? Because there is an adjunction that we show in the paper with Stovicek. Mm-hmm. there is an adjunction, so you have a functor which is a cell-quotient functor from P mod to H that has a fully faithful right adjoint that explicitly is defined as like you to any object M in the heart, you associated the restriction of the corresponding contravariant functor to P. The result is valid even when D does not have all coproducts, but in our case, it turns out that mod P is a not necessarily AB5. That was the case in the paper with Stovicek, but it is not here. And then in this case, the category is cocomplete. Mod P is an abelian cocomplete category, not necessarily AB5, but in addition, it is locally alpha presentable, where a set of alpha presentable generators is precisely given by the contravariant functors associated to the S in this skeleton of the alpha compact objects in the eye. As a corollary of this adjunction, then you have that F preserves alpha presentable objects if and only if the adjoint, the right adjoint, preserves alpha direct limits. But because G is fully faithful, this is equivalent to say that the essential image of G, that because of Gabriel localization techniques is exactly this subcategory, it consists of the P modules that the X0 and 1 from any object in T, in the kernel of F, vanish. This, so 2 is equivalent to say that this subcategory is closed under alpha direct limits. So this category of P modules is locally alpha presentable. Moreover, in my paper with Stovicek, when you apply this to the contravariant functor associated to S, this is exactly H of S. So if you prove that F preserves alpha presentable objects, you immediately have that H of S of this skeleton that we chose consists of finitely presented objects, and they generate H. So immediately you get that H is an alpha presentable, locally alpha presentable category. So our goal at the end is essentially to prove this property. But what is going to be easier for us is to prove this property 3, and we need a simplification of this property. So this is what I was saying. If any of the equivalent conditions hold, then H is locally alpha presentable. You have the argument. And the important thing is that if we put T, the kernel of the cell quotient functor, that is a hereditary torsion class in the category of P modules, any set that you could choose that generate the torsion class satisfy that image of H of G of the fully faithful right adjoint is precisely this. So in this condition that we want to check, you can choose instead of all T, you can choose as a category that sometimes you can choose it very, very small. So that is so the step 1 is that any object in the heart is the cokernel of a map of the form H of F for some morphism F in P. And this is very simple now. I mean, because of the T generating condition of P, since M is an object of the I, then you have a triangle like this, okay, where U is in U. And by the same reason, by the T generating condition of P, you have another triangle starting on the right with U, and then you somehow join. So our desired F here is exactly the composition of this map Q followed by U, by this map. So it's an easy argument. This is the easiest step in some sense. It's an easy argument to prove that when you take that F, that composition, the cone of F satisfies that when you apply the cohomological functor H is isomorphic to M. And then the cohomological condition of H, when you apply H to this triangle, you get H of this, H of this, H of this, and then H of something in the aisle shifted by 1, and that is 0. So you get that the cokernel of HF is exactly isomorphic to M. Right? Okay. The step 3, for any M in the heart, there is an alpha-directed system, an alpha-directed set, omega, and a family of morphism indexed by pair nu less or equal than omega, morphism in S, in the skeleton of this subcategory of alpha-compact objects in the eye, such that when you apply the cohomological functor H, it becomes an alpha-direct system in H. So this need not be a direct system of morphism in the ambient triangulated category, but when you apply H, it becomes an alpha-direct system in H, and whose alpha-direct limit is isomorphic to M. And the basic idea then is that you take the F that was given by the previous step. In the previous step, you have some map in P such that M is the cokernel of HF. So you take that map, and again, as before, because each coproduct is the actually alpha-direct limits of subcoproducts of less than alpha objects, you can arrange this to create a direct system, actually an alpha-direct system of morphism. Well, it's for the moment not yet an alpha-direct system, it's just an alpha-direct set omega, and then you arrange the morphism in this way, giving rise to a commutative diagram like this. So in the triangulated category, this coproduct is the direct limit of these, which are subcoproducts of less than alpha objects. The same on this part, you have that triangle. And then in particular, you have, because D alpha is closed under coproducts of less than alpha object, you can assume that X prime W and XW are both in S. And then the desired family comes by completing the following diagram. So since these are really the X prime W and XW are really direct system, then you have your maps here, these vertical maps, and then by the properties of triangulated category, you have a non-unique morphism. So this is what you do then is for any time that you have nu less or equal than W in your directed set omega, you choose exactly one morphism that completes this diagram commutatively. Okay, this is not a direct system of morphism in D, but when you apply H, it becomes so, because if you apply H to this part, then you have a unique map by the universal property of cokernel. Remember that if you apply this here, for instance, when you apply H here, it becomes here 0. So, and then by the universal property of cokernel, H of G nu W is precisely the only map that completes that. Then you have an alpha-direct system there, and now you get this commutative diagram where, I mean, from this square, from this square here, you apply H, and you obtain this square here. And you know, by what we said, that the cokernel M is the cokernel of HF is by the previous step. Now you have this. But now remember that if you restrict H to the I, then it is left adjoint to the inclusion from the heart in the eye. And as a consequence, H, this is a direct limit of objects in the eye. then H should preserve those direct limit, and then you have isomorphism here precisely because of this condition of the restriction of H to the I. Then now, of course, you are now working in a abelian category, and then direct limits or right exacts. When you apply the direct limit here, the cokernel is the direct limit, and then you have an isomorphy here because of the universal property of the cokernels. So you have an isomorphism on this part. Okay. Well, this step proves that each M in H is an alpha direct limit of objects in H of S. It just remains, in order to prove the main theorem, all what we need to prove is this equality. Okay? Okay, let's go to step 4. And step 4 is that we can choose an appropriate subset of T of this torsion class, actually hereditary torsion class, that generate it. You take as T0 those objects that appear in or have a projective presentation of, say, length 2. So these are projective alpha small objects, alpha presentable objects, actually projective alpha presentable objects of mod P. And then you can take all the objects in the torsion class that have a presentation like that. The idea of the proof, it is not have to see that T is generated by the object of T that comes, that we could call cyclic. They are of this form. They are quotient of some of these representable objects. For some, and then due to a description of this torsion class that is already available in my paper with Stovicek, essentially it says that T is the object of T appears in sequence like this, but the objects wouldn't be object of S, but okay, I will say, so the description of T that is given in that is a T consists an object, you take any mod in P, so in any finitely presented P modules, and then T belongs to this class if and only if there is a triangle such that the corresponding sequence with the representable functor is exact. Then, due to that description, you have this presentation. You have a triangle like this, which the property that the image is precisely. I mean, you want to take a projective presentation, so to say, of this object, because these objects generate T, and then you take the corresponding triangle, and you can choose it so that the image of this map is precisely the submodule N that you have here. And then, due to a result of Niemann, you have this map here comes from an alpha compact object. This is no longer in the aisle, but it's an alpha compact object, and it goes to an object in U. And Niemann says that in such case, these maps factor through some objects which is alpha compact and is in the aisle, that we can take to be in S without loss of generality. Then you get a commutative diagram with triangles in rows like this. And when you apply the cohomological, the cohomological functor here is not DH, but the generalized Yoneda functor, you get a commutative diagram in mod P with exact rows, where you have above, you have the triangle, the DH applied to this one, and in the lower row, you not the H, but the Yoneda, the generalized Yoneda functor associated to this one, and then the associated Yoneda functor associated to the lower triangle, and then you take co-kernel by our choice of the triangle. T is here, is what appears here, and now you call this T0, this object, by the description of T that that appears in my paper with Jan Stovicek. This T0 belongs to T, and you have here an epimorphic map. So T is a quotient of this T0. Since all these T's generated the torsion class, then all these T0 generated quotient the torsion class, and then it is exactly what I was saying here. So T is generated by objects that appear admit a projective presentation like that. Well, the proof of the main theorem is now by step 3, each object of M is an alpha direct limit of objects in H of S. By step 4, image of G is the orthogonal with respect to x0 and x1 to this T0, where each T0 admit a projective resolution or projective presentation like this in mod P. Then what is the consequence of this presentation? The consequence of this presentation is that now the T0 and the x1 T0 preserves alpha direct limit, because so do the covariant functor associated to these P modules. I mean, if you take this is in mod P, and these representable P modules are all of them projective and alpha presentable, and then all of them preserve alpha directed limit, and as a consequence, this T0 and x T0 preserves alpha direct limit, and as a consequence, the image of the fully faithful right adjoint G, which is this category, is closed and under alpha direct limits. This means, by the proposition that I gave before, that the Serre quotient functor F preserves alpha presentable objects, and as a consequence, you have this inclusion. But on the other hand, by step 3, we know that any object in the heart is a direct limit of objects in this category. This means that any alpha presentable object is in particular a direct limit of objects, an alpha direct limit of objects here. But because of the alpha presentability, that means that it is a summand. So any object here is a summand of an object. So what remains actually is to give that it is not only that any alpha presentable object is a direct summand of an object here. The theorem says that there is an equality. I mean, any alpha presentable object in the heart is isomorphic to an object in H of S. So that is a tricky argument. I mean, not hard, but it's a little bit tricky. And it appears it's exactly the same that appears in my paper with Jan Stovicek. And then, well, I stop here.
Thank you, Manolo. Can we all unmute ourselves and give the speaker a round of applause? Did you say you were stopping, or did I mishear you?
What?
Did you say you were finishing the talk, or did I mishear you?
No. I mean, I'm done with the talk. I mean,
Okay, thank you.
five or maybe 7 minutes before, but that's okay.
Okay,
I
thank
mean,
you. If you have any questions for the speaker, please ask them now.
Hey, Manolo, can you say
Hi.
something about the homological functor? I mean, from the Dirac category to the heart.
Yes.
Is that factor how to say this presentable?
Is what? I mean, I didn't.
I mean, is this functor presentable?
Not normally not. Normally not. Actually, well, presentable. I mean, H is not the abelian. Is not abelian group. So what do you mean by presentable?
Well, I just want to know.
Representable. That would be. What do you mean by that in this case?
I mean, for example, if we consider this, somehow can we say that H isomorphic to some home X blank like this? Is that okay? I mean, is there exist does there exist some X such that H isomorphic to home X blank?
No, I mean, what I know is that if you take, okay, I try to. So what happens sometimes is that, for instance, if you want to represent some so sometimes this is for some, but you is not the case normally. But sometimes if you put an appropriate object here, then it is representable. Of course, here, say, let's see, because here you need. Is restricted to H. So I mean, in general, I would say that, but sometimes you have something like that if you restrict to certain objects in the triangulated category. I would recommend. I mean, in the paper with Jan Stovicek, it is the final section deals with that, with some example of representability, but it in this sense. So sometimes, for instance, let's see. Just a moment. Also, in my paper with Pedro Nicolás and Sasha Zvonareva, there is some there is some result of the type, but so So for instance, if you take my paper with Stovicek, proposition 8.3, you have there a situation where you have that you take some object in the ambient, is some pure injectivity there, and then you get that in the triangulated category from to this is isomorphic, naturally isomorphic to here would be H and then H of Q here.
Okay.
So results of this sort, and actually it is one of the things that when AQ have some sort of pure injectivity, this H of Q is injective in the heart. And it is a way of dealing with, going from one side to the other. So here you have is at the beginning of section 8 in my paper with Jan Stovicek, and also you have something in my paper with Pedro Nicolas and Sasha Zvonareva.
Thank you.
Thank you. Any other questions? Anybody? So of course, as you mentioned, Manuel, in your talk, there are many examples that we know of branded categories that are well generated but not compactly generated. Have you got any special examples in mind where you could try to see what this set of generators, if the set of generators for the heart would be anything special?
Okay. There are like two directions. One, there is this paper in Invenzione by Niemann, where he proves that for a ring R that is not coherent, then the homotopy category of the projective modules is Aleph 1 compactly generated, but it is not compactly generated. And then at the end of the paper, it is an explicit choice of the set of Aleph 1 compact objects which generate the category. No? So the other source of example would be the derived category of a Grothendieck category. That is always well generated. There is always and then for instance, if you take actually our theorem says that if you take any set of objects, essentially you take the cardinal alpha, the regular cardinal that is smallest with some condition, and then you take the alpha compact object in the heart, and you apply H, apply the cohomological functor, and then you take that is your set of generators for the heart. So actually, I should tell you once you ask the question, this paper is in the archive with the title "Set Generated T Structures Have a Heart with a Set of Generators." So you can find it in the archive. And I didn't send it to a journal yet because I had to stop because it was at the end of July and I had to go on holiday. And then what remained was exactly to put some examples, just to show examples where you can calculate explicitly a set of generators in the heart, which is for a T structure which is not compactly generated. It's alpha compactly generated for some alpha. So that was what remained to be, but I've been out of research in the first semester because I was with all my teaching there. So for the moment the paper is there, but it's still incomplete. It needs some examples at the end. Mm-hmm.
I think some motivic examples would be lovely, but I don't know much about motives. Any other questions? Anybody?
Manolo,
yes.
And I mean, as your results show that if you consider the compact generated triangular category and the T structure, the compact generated T structure, then you got the heart is locally finitely presented the Grothendieck category, right?
Locally finitely presentable. That is the result with Jan Stovicek.
Yeah. So I mean, do you study the purity theory between the triangular category and the locally finitely presented category?
Oh, yeah. You should look at the paper because we've generalized very far the usual purity. I mean, the usual purity in triangulated categories is done in compactly generated triangulated category. We do it here in the paper for what we call a standard well-generated triangulated category. And that means that a standard well-generated triangulated category is a triangulated category that appears as the quotient of a compactly generated one by the localizing subcategory generated by a set of objects. This should be a set. We don't know even if these are the only well-generated triangulated categories. I mean, I think this is but it is a standard way of constructing a well-generated triangulated category. So you take a compactly generated category, and then you take a set of objects, any set of objects. The localizing subcategory generated by that set of objects, and you take the quotient by it, and that is well generated. That is well generated. And there, in that context of a standard well-generated triangulated categories, we developed a theory of purity. It's not as nice as the compactly generated one, because there could be some sort of pathologies.
Yes.
In the sense that you could have objects. How was that? So that all you take the h of all shift, and it's 0, but or better, yes, that the pure injective envelope of an object is the 0. So you can have that pathology in principle. We don't know example. Actually, in the paper we mentioned that we don't know it, but in principle, our theory of purity allows for that pathology, that you have an object whose pure injective envelope is 0.
Oh, so you mean well-generated category, not compactly generated, right?
Not compactly generated, yes.
I see. Maybe, yeah, I see. But maybe in this case, maybe I don't know. Maybe somehow maybe some lambda purity.
Some what?
Okay. Some, I don't know. I just guess maybe some notion like some, if you consider alpha compactly generated, so maybe there's some notion like alpha purity theory, alpha blank purity.
I don't know.
So,
I mean, the basic idea, the philosophy behind purity, when you go from the compactly generated world, is that a triangle should be pure when any cohomological functor takes it to an exact sequence. Any cohomological functor to an AB5 should be AB5 abelian category, takes it to an exact sequence. So that is the philosophy behind purity in say in an arbitrary triangulated category.
Right.
With coproducts, always with coproducts.
Thank you.
So there is no real translation into alpha purity for triangulated settings in the terms that you are explaining, Manolo?
Not that I know of. So it's possible that it exists, but I don't know of.
Thank you.
Thank you, Sergio. Any other questions or comments? Well, if we don't have further questions, let's thank the speaker once again.
Thank you. Thank you for your beautiful talk.
Okay, thank you very much, and see you